Namaskar and welcome to this course, this lecture on concrete engineering and technology. In the course, as we know, we are trying to study the basic principles underlying concrete science and engineering, developing a framework which helps us understand the present scenario in concrete engineering with the use of different mineral admixtures, different chemical admixtures, construction technologies, and so on. We are going through some issues in special and high performance concretes and their quality control, testing, which includes performance based thinking, durability of these concretes, and maintenance of the structures made using these concretes. To reiterate, normally concrete can be taken to be a mixture of coarse aggregate, fine aggregate, cement. Ordinary Portland cement is what we refer to most of the time in the traditional sense, and water. Even though it is becoming increasingly common to use mineral and chemical admixtures to obtain desired properties in fresh and hardened concrete, an understanding of the basics always helps in building a foundation which is required to understand some of the special concretes which we will be talking about today. Now, this slide we have seen before. It is again viewing concrete as a multi-phase composite, which shows that if we take a slice of normal concrete, what we see is that concrete can be looked upon as aggregates, or well, coarse aggregates embedded in a system of mortar. Now, if this was modeled to be like this and this was modeled to be like this, then concrete is essentially a mixture of gravel, sand, cement, water and air, which when mixed gives you concrete. The properties of fresh concrete, properties of hardened concrete are basically determined by the properties of the constituents and the proportion that we use. We must remember, in proportioning concrete, we have seen that at the end of it, all the constituents of concrete should contribute a certain amount in terms of volume to the 1000 liters or a cubic meter, and that is what we get as unit content of different materials. This again is just definitions which we have seen before. Cement and water is paste, paste and sand is mortar, mortar and coarse aggregate is concrete. There is a reason to look at it once again today, whether we want to change some of these ideas, whether cement and water alone should be called paste, and so on and so forth. We shall see as we go along. This again is the broad outline of the course, which talks of fundamentals of concrete, proportioning concrete mixes, stages in construction, special concretes, mechanisms of deterioration, reinforcement material used in concrete, and maintenance. And today the discussion focuses on special concretes. What is a special concrete? And we have tried to answer this question before. It could be based on materials that we use in the concrete. It could be based on the properties of the concrete that we are talking about. A concrete could become special because the method of placing or casting or curing of that concrete is something different, or the environment in which the concrete is cast or placed is different. What this clearly shows is that in order for a concrete to be special, it has to be different from normal, and therefore, for the materials, properties, the method of casting, the environment of casting, for each of these issues, we must have what we will define or what we understand is normal. If any of those conditions changes, then the concrete becomes special. The concreting method becomes special. Now, as far as materials is concerned, apart from coarse aggregate, fine aggregate, cement and water, we could use fibers, we could use mineral admixtures. Even if we assume that using mineral admixtures like fly ash or blast furnace slag has become common practice, either in the form of blended cements or as additives in concrete itself, there is a special issue involved when we use high volumes of fly ash, and that is possible and is done in certain specific applications. Similarly, properties. We talk of properties of concrete in terms of strength, workability, durability. Now, strength is the property that is supposed to be representative of concrete. Most concrete engineers or designers, they talk in terms of characteristic strengths of concrete, and they say, well, M40, M50 and so on. So, what is the normal range? And if it is higher than that, then it is special concrete in terms of high strength concrete. At times, we also try to develop low strength material that need not be used for reinforced concrete construction, but has certain other applications. So, that again is a special concrete. Similarly, workability. Depending on the method of construction that we use, if we are using normal methods where concrete is carried by wheelbarrows or in pans manually, then we need a certain amount of workability. But if we are trying to pump the concrete, then we need another kind of workability. We need the concrete to be flowing sometimes. So, that is what makes it special. Durability is a very, very different kind of property, and attention on durability as a property of concrete is not all that old, even though the importance of the different parameters such as the water cement ratio or the cement content, type of cement used, and their relationship with the environment in which the concrete structure is placed is age old. Specifications did say what are the limits of water cement ratio, what are the strength requirements from the point of view of durability. Of late, however, there is an emphasis on trying to test durability more directly rather than depending only on strength as an indirect measure of durability. So, this again, high durability concrete is a special concrete. As far as methods of construction are concerned, shotcreting, where the concrete is gonited onto a surface without a formwork, where the concrete is compacted using vibratory rollers, for example, in the construction of roads, these are concretes which call for special attention. As far as the environment in which the concrete is placed, underwater, hot weather, cold weather, these are situations which call for a special attention as far as concrete and concreting procedures are concerned. Now, let us look at examples of special concretes, several of them: self-compacting concrete, fiber reinforced concrete, mass concrete, high strength concrete, underwater concrete, roller compacted concrete, shotcrete, and that list can go on and on. Now, these are all different concretes or special concretes because of one or more of the reasons that we discussed in the previous slide, in terms of materials used, in terms of the method of construction, in terms of the properties, or in terms of the environment. Having said that, it is not possible to develop a special concrete purely based on one of the issues involved, or it is just not that. If we material, concrete engineering involves, from another point of view, several aspects. One of them is materials and proportioning. What is the kind of materials we use? What is the proportion that we use? What is the process of mixing the concrete? What kind of mixer, volume of mixer, method of mixing, time of mixing, how is the concrete transported, agitator trucks, conveyor belts, and so on. How is it placed? How is it vibrated? Form vibrated, internally vibrated, not vibrated at all. How it is cured, curing compounds, membranes, gunny bags, underwater, and so on. So, all these considerations are important when we talk of concrete. Now, when we talk of special concretes, this whole thing is interrelated. So, if we are talking of a special concrete from the point of view of strength, then not only the materials and proportioning of materials is different, but that has implications in terms of mixing, it has implications in terms of placing, it has implications in terms of vibration and curing. So, only a comprehensive view of all these issues will help us properly handle special concretes. I have not even talked of what is high performance concretes. Let me share with you a small digression. In the late 80s and early 90s, that is 1980s and 1990s, the high performance concrete as a term in concrete engineering was being widely touted, and there was a school of thought that at the end of it, the performance of concrete is basically strength. So, high strength concrete is the high performance concrete. So, performance and strength were related, were supposed to be almost synonymous. But there was another school of thought or another school of researchers and engineers who were working on other parameters, workability, or a concrete which did not require to be vibrated, and that was going to help us produce concrete of a more uniform quality. That was touted as performance. So, finally, what has happened is that no matter what parameter we use, it could be workability, it could be strength, it could be durability, so long as the performance of that concrete is higher than what is normally expected on that parameter, the concrete can still be called a high performance concrete. Now, we have talked of these examples as of special concretes, and today we will focus on high strength concrete. Now, let us take a look at this picture once again. Concrete, as we said, is a coarse aggregate embedded in mortar. Now, what is happening as far as strength is concerned? In normal concretes, the strength can be determined by either the strength of the coarse aggregate or the strength of the mortar or the strength of the intermediate transition zone, and that is what is shown here, and that forms just around the aggregates. That is the interface between the aggregates and the mortar. Now, as the strength of this mortar phase is increased, and how do we increase it? We know that the only way that that strength can be increased is by reducing the water cement ratio. That is, either put more cement or use less water. So, as we increase the strength of the mortar, we get higher and higher strengths, so long as the ITZ does not become a bottleneck. So, in high strength concretes, we are talking of a situation where the mortar phase is very strong. Now, the strength of the mortar phase itself depends on the porosity and the pore size distribution. more porosity than the pore size distribution perhaps. So, in high strength concretes, we try to control the porosity, which we know is related to the water cement ratio. Once we keep this in mind, that in high strength concretes, we have reduced porosity because we use very low water cement ratios. The strength of mortar phase is much larger or much more than in traditional concretes. The ITZ is also stronger. There is less bleeding in the concrete, and therefore, the ITZ formed is not that higher in water cement ratio. Then we will be able to appreciate and discuss the properties, the construction method, the proportioning and so on of high strength concretes with a lot more ease. Now, once we talk of high strength concretes, we must remember that there is no universal definition of high strength. High strength simply means high strength, but then there are different norms of what will be called or what may be called high strength. For example, the Japan Society of Civil Engineers puts down a level of characteristic strength of 60 to 100 newtons per millimeter square to be treated as high strength concretes. IS 456, the code in India, mentions 3 categories of strength: ordinary, which is M20 or well M10 to M20, standard, which is M25 to 55, and high strength, which is M60 to M80 concrete. So, we should remember that specifications such as the JSCE and the IS 456, they define characteristic strength on the basis of tests of cylinders and cubes, and the grade cannot be directly compared only on numbers. The JSCE defines these values or talks of these values in terms of cylinders with 100 mm diameter and 200 mm length, whereas IS 456 talks in terms of a 150 by 150 into 150 cubes. And now, for the same concrete, if we take cylindrical specimens and we take cube specimens, the strength determined is different. Cubes are stronger by about 15 to 20% compared to cylinders, and therefore, what we are talking of M80 here based on cube strength is at about 15-20% lower as far as the Japanese standard for high strength is concerned. That is something which we must bear in mind when we are talking of high strength concrete. As to who is talking about high strength concrete, what specification provisions will apply may depend on the specification will depend on one specification to another. For a particular strength, one specification may say that provisions relating to high strength concrete apply, whereas another may say no, they do not apply, it is just normal concrete. As far as concrete strength is concerned, we should also remember that concrete structures are built in the field. They are normally not factory made products, and therefore, the strength we are talking about, even though is based on laboratory tests of cylinders and cubes or whatever the specifications may require, what the engineer keeps in mind is that finally, the strength has to be achieved in the field with conditions of transportation, placing and curing as may be applicable in the field, the technology which is available in the field. And that is why different specifications which are drawn by different countries naturally take into account the kind of construction technology that is normally used. Nobody stops them from using different technologies, modern methods, old methods, but the specifications are written from the point of view of normal construction, and that is what is at the back of the mind of people who write specifications and make a statement as to whether or not provisions for high strength concrete will apply. So much for the definition of high strength concrete. There is no uniform definition, there is no universal definition, and different specifications depending on different conditions that the writers of those specifications feel like they lay down different benchmarks which will help us define high strength concrete as far as that specification is concerned. Now, what are the characteristics of high strength concrete? High strength concrete is characterized by low water cement ratio. Naturally, unless we lower the water cement ratio, the water that is available beyond that required for hydration of cement cannot be controlled, and that excess water is the one that is responsible for the creation of pore spaces. So, if we are able to reduce that excess water, we have basically created a framework where the amount of pores generated is less, and if the amount of pores generated is less, the porosity is less and the strength is high. So, high strength concrete is characterized by low water cement ratios, and these low water cement ratios typically would mean 35% and below. How can we reduce the water cement ratio? One is to reduce the water content, but we cannot reduce the water content below a certain level, because that is the minimum required for workability and so on. And therefore, the only other option that we have is to increase the cement content. So, the high strength concrete is characterized by high cement content or use of other powders, whether cementitious or not. Using high cement content has its own implications in terms of heat of hydration, in terms of economy and so on. But since we need not only the cement, but also we need to increase the paste content, as we will see later on in the discussion, we very often use mineral admixtures such as fly ash or blast furnace slag or silica fume to increase the strength. Some of these products contribute to the strength by the formation of the CSH gel in the secondary pozzolanic reaction, or they simply occupy the spaces in the pore space, reducing the porosity, and else they just contribute to the paste content by sheer presence. Things like stone dust would be in that category. They do not possibly participate in the pozzolanic reaction, but their fineness is such that they are, or they can be, counted towards paste content, which is also required to be increased as far as high strength concrete is concerned. One of the options we mentioned was reducing the water content. Now, reducing the water content can be achieved through high doses of superplasticizers. This we have seen an example somewhere, that if we are able to use a certain amount of superplasticizer, we can reduce a certain amount of water demand for a given level of workability. So, if we want to reduce the water content for a given amount of workability, using superplasticizers is almost the only way out. A lower size of the maximum size of coarse aggregates. As the maximum size of the coarse aggregate increases, the strength tends to reduce. The defects that are formed as a result of the presence of these large coarse aggregates are bigger, and they tend to become the weakest link in the whole strength chain. That is why we try to reduce the maximum size of the coarse aggregate as far as high strength concrete is concerned. Once we reduce the size of the coarse aggregates, we increase the surface area, and once we increase the surface area, we need more mortar, more paste, and that is what relates to the use of mineral admixtures and other powders in high strength concretes. low air content. High strength concrete is also characterized by a low air content. We shall see in a slide what are the provisions that are related to air content. There could be a lot of other properties which we can list and enumerate as far as high strength concrete is concerned. Now, coming to the air content in high strength concrete, it is known that entrainment of air tends to decrease the strength. Even though when we do air entrained concretes or when we make air entrained concretes for different reasons, we do not explicitly take that into account because of other benefits that follow, but indeed it is logical that air at the end of it contributes or causes some kind of voids to be created within the concrete, and that obviously tends to decrease the strength at least to some extent. Now, as far as high strength concrete is concerned, that is quite an unacceptable position, and therefore, we must try to control that. In environments with cyclic freezing and thawing, adequate air entrainment is needed from durability considerations, but prescribed lower limits on air content could be, if no freezing and thawing is there, then of course 2%, but in case freezing and thawing resistance is required, then we can see here that the air content requirement goes down as the strength or the required strength increases. So, basically the designer makes a choice that if we push the strength higher, we have to sacrifice the air content. We cannot get the benefits of air content all the time. So, as far as the normal concrete is concerned, yes, we can have 5% or 6% air sometimes, but the moment we get into high strength concrete or strength ranges in these range here 60, 70, 80 and so on, then the air content has to be restricted. Then let us talk a little bit about some of the considerations that weigh on the mind of an engineer as far as high strength concrete is concerned. Because of the low water cement ratio and the high cement content, high strength concrete could have large autogenous shrinkage, large amounts of heat liberation on account of heat of hydration. Traditionally, mass concrete was defined as concrete where the structure was large or the pore volume was large, to the extent that the heat dissipation that took place from the surface was not sufficient to handle the heat liberated on account of heat of hydration of cement. In the case of high strength concrete, even with adequate surface area, because the amount of heat liberated is large, because the cement content is high, even concrete members of the size that would normally be not considered mass concrete would have to be treated with provisions of mass concrete. Once we have mass concrete related considerations or shrinkage related considerations arising out of the high amounts of cement, we could have cracking in the concrete, non-structural, but cracking nonetheless. And that is something which will require special attention from the point of view of water tightness, durability and so on. So, high strength concrete is very good as far as durability is concerned from the point of view of the fact that porosity has been reduced, but if we allow cracks to form in high strength concrete, then the whole purpose is lost. And that is something which as concrete engineers we must keep in mind, that using high strength concrete or having a characteristic strength of concrete as a certain number is not really good enough to ensure high durability concrete. For durability, we need to do a lot of other things other than strength, such as controlling cracks and so on. Further, strength of concrete in the structure itself is of concern given the difference in curing regimes, the scale of casting and so on. In a normal concrete, if we do the quality control using cubes which have been cured underwater versus a situation where a certain member has been cast and the concrete is sitting here. In normal circumstances, the environment here as far as temperature and so on is concerned is not so different from this atmosphere. But when it comes to high strength concrete, the temperatures here are higher than normal. And therefore, when we cure the cubes here, the curing regime of cubes which are used for quality control is quite different from the curing regime or the environment surrounding the concrete in a high strength concrete structure. And this difference starts becoming prominent and has to be accounted for in our quality control procedures and also in attempts to actually figure out what is the strength of concrete in the structure. Now, low water cement ratio and high cement or cementitious material content are two sides of the same coin, and we have already talked about that. With a smaller size of coarse aggregates, the demand for high mortar or paste content also increases, which is related to the above. That causes us to use more powder in the system, and the concrete becomes more homogeneous in the absence of the larger coarse aggregates. See, concrete is not a homogeneous material at the millimeter levels. It can be considered homogeneous if we consider reasonably larger sizes or reasonably larger unit sizes, and that unit size which is required to be considered for concrete to be assumed to be homogeneous is related to the maximum size of the coarse aggregate used. If we are using large coarse aggregates, then we will have to consider a much larger area in order to say that, okay, if that area is replicated all over the place, the concrete is homogeneous. If those of you who work or who have a background in finite element analysis would understand this concept very simply. In order to assume that concrete is homogeneous, you are making an assumption that the aggregates and the mortar and the ITZ have all the same strength, which is obviously not true. So, if we are able to remove the larger coarse aggregates, the concrete becomes more homogeneous, and also the gap between the strength of the coarse aggregate and the mortar matrix is narrower. So, from normal concretes or in comparison to normal concretes, high strength concretes are more homogeneous. Now, this homogeneous business or this concrete becoming more homogeneous has very interesting implications. Crack growth becomes more rapid and the concrete is more brittle than normal strength concrete. In fact, the crack growth in concrete and the stress strain curve. The stress strain curve is only the relationship or a representation of how the material deforms as stresses are applied, and as stresses are applied, more cracks are formed in the system. So, indirectly the stress strain curve is a representation or can be taken to be a representation of the crack formation and crack propagation in concretes. Now, as far as normal concretes are concerned, if we look at a normal concrete, there are aggregates and we have mortar, and these are the aggregates. Now, if load is applied on these, if load is applied on this concrete and we get the stress strain curve, we know that these are, so this is one of the model stress strain curves which are used. Why is it non-linear? Because as micro cracks are formed here initially, they tend to connect at the coarse aggregates. Some kind of crack propagation takes place through the intermediate transition zone, and then larger cracks are formed, which cause the concrete to fail. In the case of high strength concretes, this process where cracks have a stable growth, it does not exist. So, if we look at the stress strain curves of concrete and paste, this is the stress strain curve for concrete and this is for paste. Because the material which is paste is more homogeneous, the crack propagation is rapid and the material is more brittle. So, the high strength concrete tends to come closer to paste, and therefore, and that is something which we must keep in mind when we talk in terms of properties of high strength concrete. The principles of subjects such as fracture mechanics becomes more relevant in studying high strength concretes. Fracture mechanics is the science that studies crack formation, crack propagation, and so on. If you read the literature on fracture mechanics, you will realize that the whole assumptions, the whole set of assumptions made in fracture mechanics are more valid when we are talking of high strength materials, more homogeneous materials within concrete than normal concrete. As far as properties of high strength concrete is concerned, is the fire resistance, which is reported to be suspect due to the difficulty in the movement of trapped moisture at elevated temperatures. Concrete could have some moisture trapped inside, and that moisture must be able to escape in the event of fire, because the temperature is rising or the temperature in the concrete rises. Now, in the case of high strength concrete, because of a different kind of pore system, that water finds it difficult to escape. And if the water cannot escape, it gets converted to vapor, exerts pressure and causes local, well, if you want to call them explosions, which damages the concrete, and the performance of concrete at elevated temperatures under fire becomes suspect. Coming to the properties of high strength concrete, let us talk in terms of consistency, which is the property for fresh concrete. Let us talk of a regime where the slump is less than something like 21 centimeters or 200 mm or 210 mm or something like that. At this level, the sand content in the concrete is comparable to normal concrete, and of course, that concrete has high range water reducers, and the consistency can be evaluated using the conventional slump test, and that is what is used in factory products. Whereas, if the slump becomes more than 24 centimeters or 240 mm, then we cannot really use slump as a measure for the consistency or workability of the cement, or the consistency or the workability of the concrete, and we get involved with the slump flow regime. And this is what happens when we are talking of a higher sand content, that will obviously imply a higher mortar content, which is there in the case of concretes with low water binder ratios, as high strength concretes have, using air entrained high range water reducers and so on. And this is the kind of concrete which is used when we are trying to develop self compacting high strength concretes. So, there are two distinct ranges of consistency. One is where by the sheer use of superplasticizers or high range water reducers, we are able to get to a level where the strength becomes high enough for the concrete to be called high strength concrete. In another situation, we have gone beyond that range where slump can be used, and we must use slump flow. And depending on where we are using the concrete, in the factory for making precast products, or whether it is being used at site. We need to make our judgments, we need to proportion the concrete in a certain manner and so on. Now, between 21 centimeter and 24 centimeter, we need to make a judgment. When it comes to construction using high strength concrete, we must remember that the concrete is now characterized by the presence of a large amount of paste or a large amount of mortar, which makes the concrete very viscous. And once the concrete has become viscous, then needle vibrators are less effective than in the case of normal concrete, and therefore, the spacing and the time of vibration needs to be carefully chosen. The bleeding in high strength concrete is less. The surface should be protected against drying, because the surface which is susceptible or vulnerable to drying anyway, if that happens in high strength concrete, the reduction in strength could be very drastic, and that is why we must make sure that the surface is protected against drying. Finishing and traveling is difficult. Pumpability should be ensured before construction, because once the concrete becomes viscous, pumping it is not really the same thing as pumping normal concrete, which has a certain amount of flowability. Now, let us talk a little bit about determining the strength for high strength concretes as far as quality control is concerned. One thing that comes to mind is the age at which the quality control should be carried out. Since mineral admixtures are often used along with Portland cement, strength development, at least in the initial part, could be slow, and this could be accounted for in some manner by allowing quality control tests at an age later than the normal 28 days, say 56 or 91. Now, there are two arguments which go in the favor of such a treatment. One is the fact that, well, we are using mineral admixtures which possibly will have pozzolanic reactions and contribute to strength development at a later stage, and therefore, we should do the quality control at a later date. Secondly, the structures are very often not really loaded in a month, and therefore, there is no harm in saying that we will wait for more strength development to occur over a period of 2 months or 3 months before we carry out a final check as far as quality is concerned. Now, what is the other side of the story? The other side of the story is that even though even 1 month is late or 1 month is late enough, if we wait for 2 months or 3 months and then find out that for some reason the strength has not reached the level where we thought it would, the construction process would really be in a big jeopardy, and therefore, a very careful thought has to be given. Science, or scientifically speaking, yes, there is reason to believe or reason to say that yes, in high strength concretes, because we are using mineral admixtures, we can go ahead and use a longer time for quality control tests. And we have already talked about comparing the strength from cubes with that in the actual structure. We have talked about the stress strain curve, which is steeper than normal concretes. Another thing that happens is the capacity of the machine which is required is much higher in order to carry out the tests. As the strength increases, we need machines of higher and higher capabilities to be able to carry out the compression test, cause those specimens, whether they are cubes or cylinders, to fail, and that becomes a problem in high strength concretes, because we do not have so many machines, or we may not have so many machines in the neighborhood of that construction site to be able to carry out that test. Not only the strength or not only the capacity, but also the stiffness of the machines and other testing parameters, the rate of application of load, condition of the specimen, all these things become very, very important when we are talking of quality control of high strength concrete from the point of view of testing. Now, there can be an argument which is built up for a smaller size specimen, which will help us from the point of view of the capacity of the machine required. We use, for example, in India, 150 mm cubes, or somewhere we use 10 centimeter by 20 centimeter cylinders. That is related to the fact that most of the time we use 20 to 25 mm kind of aggregates. So, if we are able to reduce, and if we do reduce the size of aggregates being used as far as high strength concrete is concerned, there is a case that the size of the specimen used may also be appropriately reduced. You can imagine that if we are using 15 centimeter cubes, we are talking of an area which is really about say 225 centimeters square, whereas if we are able to reduce the cube size to 10 centimeters by 10 centimeters, the area of the cube is only 100 centimeters square, which means that if that was acceptable from the point of view of the maximum size of the aggregates and so on, we could make do with a machine which has less than half the capacity. So, these are the kind of things that as engineers we need to decide as far as testing of high strength concrete is concerned. Now, failure could be explosive, and therefore, particular care should be taken to ensure appropriate safety checks when testing high strength concretes. Because of the brittle nature of the high strength concrete, at failure the material may explode and particles or pieces of the concrete may fly out, and therefore, we must try to make sure that people in the neighborhood or the equipment in the neighborhood is not damaged, which means that we need to have a cage in which these specimens are tested to failure. As far as durability of high strength concrete is concerned, aggregates should be checked for reactivity as the cement content, and therefore, the alkali content could sometimes becomes high. Usually aggregates are not rigorously tested, because at least from the point of view of strength, because the mortar phase is so much weaker than the aggregate, but not so much in the case of high strength concretes, and therefore, we have to be more careful as far as the choice of aggregates, the particle size distribution, the strength and so on is concerned. As far as reactivity is concerned, again they have to be checked, because even marginal aggregates can have problems because the high alkali content in the concrete, because the cement content is high. Because the dense pore structure, carbonation is not really a problem. Since high strength concrete is often used in harsh environments, though chloride ingress may not be a problem, but chlorides within concrete should initially be controlled, because it becomes more and more difficult to get the for there is no way that anything trapped inside can move out, and if they are part of an admixture and so on, then whatever we use will remain trapped inside. So, that is something which we have to bother about. Cracking should be controlled to ensure water tightness and durability against freezing and thawing, which is related to air content, and special attention should be paid to fire resistance, as some of the reports suggest explosive failures at high temperatures. And lastly, coming to some simple things related to design using high strength concretes, we must remember that empirical equations for estimates of properties such as the modulus of elasticity, the tensile, bond or shear strength are not valid, and efforts need to be made to get these through experiments. Very often a specification will tell us that E can be taken to be 5000 root of FCK, or the modulus of rupture can be taken to be something related to FCK or the root of FCK. These equations are valid only for the range in which they have been tested, and since the data for high strength concretes is not all that voluminous, it is not prudent to use these kind of correlations which exist for normal concretes for high strength concretes as well, and that is something which the designers have to keep in mind. Also, the lack of ductility of the concrete needs to be factored in. Before we close, as usual, we will have some questions. which we should try to answer to improve our understanding of the issues that we have talked today. Study the applications of fracture mechanics principles to concrete engineering, especially in the case of high strength concrete. You will find that a lot of researchers have tried to apply fracture mechanics principles to paste and mortar, and in some cases high strength concretes. What are the kind of parameters that they use, how they evaluate them in fracture mechanics, and so on. List and study proportions of high strength concrete used in different projects around the world. High strength concrete has been used in a large amount of projects across the world, where the quality control has been carried out at different ages, using different sizes and shapes of specimens. So, if we make a list of that, we will observe that there is a difference in the parameters such as the maximum size of the coarse aggregate used, the details of the paste composition in terms of the supplementary cementitious materials or mineral admixtures used, the superplasticizers used, and so on, the testing and quality control procedures, and I would like you to list and study special provisions for the design of concrete structures using high strength concrete. And with this, we come to the end of the discussion today. Thank you.